So we start the second half with a talk from Professor Egemen Kolemen. He has a joint appointment among the Andlinger Center, Mechanical and Aerospace Engineering, as well as Princeton Plasma Physics Lab. His PhD is from Princeton, and then he'd spent some time at the PPPL after that. And he's interested in applications of dynamics and control theory to experimental plasma physics. And he conducts these experiments and control system design at national and international fusion reactors. So let's hope that we don't have to wait for 30 years. In 10 years with the work like he's doing, we'll have an economical fusion reactor.
Pretty soon. Thank you very much. I'll present a bit of an introduction, and then I'll talk about what I'm doing with my students here. Okay, so you were just asking when are we going to get fusion? When I get this question, I say, well, we've been always using fusion. So when you use a solar panel to make electricity, that's the fusion energy in the sun that's converted to radiation that you turn into electricity with your solar panel. And even when you're using fossil fuels, that's basically fusion energy stored from a million years ago that now you end up using. So we are using fusion energy. The question is, when are we going to start using fusion energy directly? So that's what we want to do. Make a sun on Earth so we can make electricity out of it. So to do that, unlike fission, which splits up uranium, we want to fuse two particles. And the easiest ones to fuse are small particles. So we use hydrogen and hydrogen's isotopes. So the two isotopes we use are deuterium and tritium. So this is like extra neutron and extra 2 neutrons to hydrogen. And when we fuse them, we make helium, a neutron, and a lot of energy. So we have a lot of deuterium in the world. So there's more than enough to last us until the end of the Earth. But we don't have tritium. So we need to make tritium. So the way that works is when we fuse deuterium and tritium, we get a neutron. And if you put a blanket of lithium around your reactor, this neutron hits that lithium and makes tritium. So then you can feed that back to your loop, and then you can get a deuterium and tritium reaction and make energy out of that. So the idea is that you confine a plasma. Plasma is really hot, tens of millions of degrees, and you have ions and electrons that are floating here, and it's like the sun. And you put in deuterium and lithium, which we have a lot of, and in a roughly 6-meter size machine, you make energy, and then you convert that, the neutrons that are hitting the wall makes heat, and that heat is converted to electricity with a regular power generator. So that's the idea. So, but to do that, first you need to make the sun on Earth. How do you do it? Well, the way that we are working on is the magnetic confinement. So if you look at a magnet, this is the South Pole, this is the North Pole, you get a magnetic field, and electrons and ions end up gyrating, spiraling around the magnetic field. So they're confined. They stay here. But at the end of it, they hit the end, and the confinement ends. So what we end up doing is, instead of having a linear machine, if you turn it around and make it a donut, then you can confine the plasma, so these electrons and ions are gyrating here, and you just stay there for a long time. So this is called the Tokamak. It's a Russian name for, basically, it's a torus machine. And we make the magnetic fields using these coils, and we run currents through it, and we can confine the plasma. So we've been doing this for a while now. It started in the 50s, and if you look at 1970 to 2000, you can see that the fusion power we're making, this is the deuterium, tritium energy we're making, has been increasing exponentially, and we reached 10-20 megawatts level. And one of them is the TFTR machine that we had over at PPPL, which is across Route 1, which got up to 16 megawatts of power. And so now that we show that we can make fusion energy, we want to show that we can make fusion energy, net fusion energy, to make electricity out of it. So to do that, international collaboration have been put together for a machine called ITER. So this is the drawing of ITER machine. And for the size, you see a person here. And this is this machine is being built in France by a collaboration of US, EU, China, India, Russia, and South Korea. So it's the most expensive science project that has ever been taken over by the world. So it is a big project. And you see the site here. This is an old photo. Now there's much more structures there. Hopefully we're finishing it and we'll start running it in the 2020s. The aim of this reactor is to make net fusion energy. So we're going to put in 50 megawatts of power, and we want to get 500 megawatts of power. So that's Q, we call 10 times more energy. And this will show that fusion energy can be used as a power source. And then after that, we want to build electricity power plants. This is just to show that we can do it. So what do? I work on different machines on Tokamaks and for around the world, the San Diego, Princeton, Korea, and China, to understand some of these issues we have and find engineering solution, applied solution to the fusion. I mostly work on control, and we try to develop control systems and control solution to plasma issues. And we have small experiments as well that we work on. So the main issue I focus on is the heat flux problem. So we're making a big sun over here, and these particles, the plasma particles, are really hot. So when they're confined, this is what they look like. This is the outside of the wall, and in here, I'm drawing like a sketch of what the plasma would look like. These are concentric circles of confined areas, and if everything was confined, this would be it. But what happens is that some particles have to drift out. They don't confine forever. And when they do drift out, the red arrows here are showing what the lines they follow. Because of the magnetic fields and the way it works out, they drift out and just follow the last closed flux surface and end up at a place called what we call diverter, in a small area. They don't just spread all out. So just sometimes people get confused. Neutrons are going all around. We're not talking about the neutrons that produce the energy. This is the plasma that's unconfined, that's drifting out. So if you look at the image, this is an image from Mas at Tokamak, and this is what they look like. So this is the confined area, and the particles, the light shows that the particles just go into this leg here. They don't spread out too much. So what happens? Well, they're all coming, particles, and the heat is coming to a small location here. And if you look at the heat flux, megawatts per meter square here, you get a big peak. So this peak is not good because it will melt or damage the materials. So for example, for ITER, for 500 megawatts, we get 50 megawatts peak power, and we can only really take up to 10 megawatts with the materials we have right now. So we need to find new solutions. So if we don't find those solutions, what we end up getting is basically a plasma torch. You have huge amounts of plasma power coming into place, and plasma torch is used for cutting metal. We don't want that. So what we do is we work on a bunch of things. First, we want to simulate how on a high power plant, which doesn't exist, which will be built, what the heat profiles are going to look like. So we run complicated simulations because there's magnetic fields and all that, but you have ionization and radiation and so forth. And this is a simulation that we did, and it shows D3D, which wants to make an upgrade to 30 megawatts of power, how the peak heat flux would be for different densities. This is density, this is the power input. So 30 megawatts, you're somewhere here. And the peak heat flux is shown in the red, so this is below 10, this is above 10. So it's basically marginal if you wanted to operate this is for D3D, so not the ITER. So what can you do? So one solution we've been looking at is using magnetic control. So this is basically like you have a wire. If you think of this wire as the plasma, it's electric, and there's a current running through it. If you run a current through some other material, because of the magnetic fields, you get a force. So you can bend the plasma using magnetic fields and currents. So what we did, this is an experimental result from the 3D, is we changed the flow that's coming in here by changing the electric field here. And instead of having this one peak, we can turn into two peaks or spread it out. So we were able to get a 2.5 times decrease in the peak heat flux. So this is everything stable, steady state, and nothing exciting is going on. But we do have more exciting things in plasma. We get instabilities. Plasma doesn't really want to be confined, so it tries to find ways of getting out of this confinement. So we want to avoid these instabilities. The reason is, let's say you have a stable equilibrium plasma, and you don't do anything to it, and it might drift into an unstable equilibrium. This is how it happens in a second time frame. But once it gets into this unstable equilibrium, you see this, it's kind of twisting itself. Once you get into unstable situation, within microsecond scale times, it can disrupt. And all the energy that's confined in the plasma now hits the wall. So in addition to that small heat we're talking about, this is way more than that. So what we do is we solve this is Maxwell's equation, some other equations in there. We get diagnostics, we solve the equations, and try to understand where the stable region is and where the unstable region is in real time. So apparently we're using 1990s PCs. Hopefully we'll use better computers next time. But so we do that. We have a bunch of computation. We develop new algorithms to steer the plasma away. So this is assuming everything works. Well, not everything. You cannot always get out of instabilities. There are some instabilities that we can't really avoid. So one of them is this edge localized mode. So this is the plasma again. And I'm going to show you a video of the edge localized mode. So you see that there was a big, all of a sudden, energy dissipation. So it will come up again. Okay, so you saw that there was and when that happens again, look over here. You see when that happens, you have a heat flux, increased heat flux. So this mode at the edge puts out a lot of plasma and it hits the wall and increases the heat load here. So there's ways of looking at this. You can avoid it, or what we do now is we look at reduce the elm size. So instead of having this one big instability, can we split it into, let's say, dozens of small ones so that the heat flux is so low that we don't care about it? So that's what we do. Instead of one, we want to have multiple. So for that, we use granule injectors. So this is basically like a baseball bat. We have a material that hits the granules, and then these millimeter-sized materials fly in, and then they do two things. They feed the deuterium and tritium, and at the same time, they can induce these elms. So what we can do is then we can make more of these and smaller heat fluxes. So this is a simulation that we've been doing. So the particle is entering here, and as it's entering, you're seeing the plasma pressure profile, and you can see the plasma pressure is changing. So this is not that exciting for you. You see some colorful plot here, but based on that, we can find when the instability hits, and then we can optimize the size of these things, the speed, angle, and the period, so we can reduce the peak heat flux as much as we can. So this is what we've been doing, and looking at different materials as well. So another thing is, so let's say you are not able to suppress these, so you are not able to avoid these instabilities. So what happens? You want to suppress them. Suppressing is you got the instability, you want to turn it off before it gets too big. So for this, an example is the island instability that we see here. So there's if you look here carefully, you will see a 3-1 island. So what we do there is we diagnose it, and then we control it using microwaves. So we have a 3 megawatt microwave system. Basically, this microwave system goes into the launcher. We have mirrors, and then we can launch it to the location we want. And we can zap the instability. So basically, if you have the instability, maybe you can kill it before it gets too big. But what if you can't do anything? So this is an example from JET, where the heat load on the tungsten, they just made this on purpose, made a dent here to see how the heat flux affects the material. So you see this tungsten starts melting as the heat flux goes in. So if you can't do anything, you will have something like this. Well, so this melted tungsten gives you the idea, well, maybe we shouldn't use solid materials. Maybe we can use liquid metals. So trying different materials. For this, we have an experiment called liquid metal experiment. So this is the plasma again, and this is the diverter region, what you're seeing here. And what we want to do is run liquid metal over here so that we can take the heat out. And if it's liquid, it's not going to melt anyway. So for that, we have an experiment. We have liquid metal going through. We have diagnostics that are looking down with IR and so forth. And we try to understand and control the fast liquid metal flow. Fast meaning up to 10 meters per second. So the idea here is that we have magnetic fields. So the magnetic field is inboard here. And we run currents through the liquid metal to get J cross B. You get J cross B forces. And these forces can enhance heat transport and push liquid metal to the wall. So it sticks, it doesn't just splash. And we can control the flow and the heat flux. So I'll show you an example of heat flux, how it changes the heat flux, how we can control it. So this is the thermal camera looking down. And the red is hot and the white, the yellow is, blue is cold. And now the current is off. And when we turn on the current, you see that this redness goes away because we can enhance the heat transport. And this is useful because we don't want this material to boil. So based on this, we've been looking at alternatives, and FLIT, flowing liquid metal torus experiment, which we're designing the flowing liquid experiment. This is our design. We're trying to develop the system, technology for this, and understand the physics. And this is what part of our area is looking at to make this new machine work. And I'll end with today is a great day. We have too many grand openings. NSDX upgrade is a big opening today as well. And Secretary of Energy and Senator Booker is going to be at PPL today. So I'll have to leave to go there. But the main reason they're here is this upgrade, which is apparently it costs roughly the same as the building, the Andlinger building. So, about the same. Hopefully we'll be able to do great experiments there as well. Thank you.
Hi, Sharon Adarlo at Andlinger Center. I was wondering, there's been a number of general, fusion energy startups, and from your vantage point, what do you think of their claims of being able to, have net fusion energy?
Yeah.
Their claims of getting it cheaper and faster here compared to government-funded programs.
Well, there's two parts. One is we're always happy money coming into fusion from any direction. So, if people want to spend money on understanding fusion and trying to develop new ideas, that's great. And we do work with them. If you look at the people that are working in those companies and the advisors, you'll see a lot of our colleagues. So we try to help them as a group and at a personal level. But, because they have to sell their ideas, unlike a national lab, we don't have to, really make money out of it. So sometimes you can see a bit of overselling what they might be able to achieve. So we don't want to say anything negative about what they're doing, but, because they want to make money out of it, you have to be more careful about, putting where you want to put your money. But a lot of the research they're doing is good. The claims might need a bit more. Some of them need maybe a bit more scrutiny.
This is Vinod Gupta from Princeton. I'm wondering how safe the Tokamak is. I mean, it's a huge amount of energy in plasma. If accidentally it escapes the walls, how big is the safety concern for the lab?
I think after me, Rob Sokolow and a few students are going to talk about the fusion energy, this that they wrote. I should have introduced that. But Rob, are you going to talk about this kind of issues or not?
You should answer it.
Okay, all right. So the main thing is that this is nothing like a fission reactor explosion. It will, first of all, there is no runaway reaction here. The moment your control goes away, there will not be anything. So the only problem then is whatever is the chemical things you have. And most importantly, we have tritium. So the biggest problem would be tritium escape. Tritium is nuclear material, obviously, but it's not. It is not as a big deal as some of the fission outputs, you would say. And the amount of tritium that we have on the facility is basically decided by the people who are running it. So we do not have more production of tritium after the explosion, they would say. So I don't have the exact numbers, but I think you do not need like an evacuation plan or something like that you would have on a fission reactor. Yeah. So you can look at all that information.
Yeah. Quick question about your liquid metal experiments. What
Sure.
metal and why?
Well, we want to use lithium in the long term, and because lithium has a lot of good properties, it's low Z, and it's good for the. If it gets mixed in the plasma, it doesn't affect it badly. So we want to use lithium, and it has, it's liquid at 300 degrees or so. But lithium is a bit hard to work with. So most of our experiments we run with gallium or gallium, and we do have small lithium experiments. We're building a new building, hopefully, that will be dedicated just for, running liquid metal, so like lithium. Because our normal labs are in buildings, and you're not allowed to run big amounts of lithium in a building where people are, working. So we're building a separate place where we can hopefully run that.
I'm Peter Giller. I'm a developer of offshore wind farms affiliated with the Blackstone Group. I live in Princeton and I have friends who work in this field. I understand very little about it. When I talk to my friends, they say that the Tokamak approach is a wrong approach. It will never really be industrialized. Are there any thoughts about using a totally different approach than Tokamak?
Well, I didn't talk about it here, but we have a lot of work on stellarators. I don't know if you heard about it. Germans have built this W7X new stellarator. They're trying to study that. And some people believe that stellarators are a better solution to fusion. But if you look at it, I think at least, 90% of the problems that you have with any type of fusion reactor is roughly the same. I mean, there's some physics that are a bit different, but the heat flux problem is the same. So I work with the stellarator people on the heat flux problems. It's, you know, the first order, they're the same sort of problems. So when we're trying to find solutions, I think if we were to make the Tokamak work, but it didn't work that great, moving from that to stellarator or some other design is going to be minimal effort. So I think developing the technologies just works for everybody.
Any more questions?
Oh yeah, sorry.
So the heater,
Yeah.
how long will that operate? Understand the input and output energy.
How long will it operate? You mean like seconds wise? So it's how many minutes is it? I want to say 10 minutes. Is it 400? It's 10 minutes. Yeah, 8 minutes or something like that. At a time. And so, yeah, I mean, the main issue there is that we need to run currents through the plasma, and you do that ohmically. So you need to run basically. But now people are designing ideas for demonstration power plant that run much longer, some like months at a time or something like that, or stellarators which just run continuously. So, but the main thing about ITER is that it is the safest. Well, it is believed to be the fastest way to showing that you can get big power gains using fusion, so that we can show the idea and move on to building a reactor of some sort. So,
If you can do 400 seconds, what's the leap to having it?
So the biggest problem we see is, I mean, if you look at some of the machines like W7X that run for too long, 20 minutes is the breaking point. After 20 minutes, it doesn't make a big difference in terms of materials. You can run 20 minutes, you can run 200 minutes or 2,000 minutes. A lot of things kind of get stabilized. That's at least the knowledge I have means that if you can make things work for 20 minutes at a time, 1,000 times, you're pretty much set to be able to run a reactor for longer times in terms of the material shrinkage and all that sort of issues.
Okay, thank you.
Thank you.